Hello. I have to leave here at like 5 for another conflict. Is that okay?
Sure.
Okay, thank
Yeah,
you so
no
much.
problem. Already, so we are on time. So let's start. So I left you in this slide in last class. So I'm going to show you without doing the experiment whether some salts are soluble in water or not soluble in water. Just looking this chart, yeah. So I told you almost all salts of sodium, potassium, and ammonium. So whenever you see this kind of thing there in the compound, they are definitely soluble. For example, you have Na there, and you have some other compound, other element like this. So they are talking about Na. So look here. So if there is Na, and you see this kind of the material sitting with the like the Na. If there is Na, everything is soluble. Everybody got that? So that's how we did this table. How about this K plus? So if you see K here, and let's say you want to write something there, so maybe Kf is here. So this is soluble. You see the K there. So if there is a K in that potassium in the salt, that's also soluble. Everybody got that? If one thing is there, that's soluble. Let's talk about this NS4 there. So if you see NS4 there, NS4, and let's say OH is sitting there. So you see there's soluble, NS4 is soluble there. So anything sitting here, this compound must be soluble in water. That's how we read this table. Everybody got that? So how about down here? So let's talk about one here. So I'm going to pick NO3 here. So if you see any NO3 here, so for example, there is NO3 and NO3 is sitting with something else. I don't know what it is sitting with. So I'm going to write Cu here. So there is NO3. So this compound must be soluble. Everybody got that? So like that. Another in this column, in the second column, you see there are chlorine, chloride, bromide, and iodide here. So let's look at one of those. So I'm going to write the iodide. So there is I here. So in front of I can write anything. So maybe I want to write, let's say, RB. So you see, I is here. So definitely this compound is soluble. Everybody got that? So since there is I, so anything that has I is soluble. Now let's look some exception here. So if you see something like this, so there is an orange box here. So this orange box element is combined with something like this. So let's say that orange box element one is Pb, and this guy is sitting with some of these material, maybe chlorine, bromine, or iodine. So like that. So if Pb and I are sitting together, that is insoluble. That exception means that is insoluble. Everybody got that? So everything sitting with Cl, Br, and I is soluble. But if Cl is sitting with Ag, that's HCl, not soluble. Hg2 sitting with Cl, not soluble. Pb sitting with any of these elements is not soluble. That's how we read this table. Everybody got that? So like that. So let's look next one here. Sulfate. Sulfate, every sulfate is soluble. So let's write one sulfate. So I'm going to write one sulfate here. And so they are talking about the sulfate, SO4, 2 minus there. So I'm not even writing that 2 minus here. Let's write something here sitting with SO4. So I'm going to write Fe here, FeSO4. Would it be soluble or not soluble? So they are saying everything that sit with sulfate is soluble. Everybody got that? But if you see something like this, let's say Ca sitting with sulfate. So if you look the Ca there, CaSO4. So they are saying this CaSO4 is not soluble. Got it? SrSO4 is not soluble. Ba sitting with SO4, that compound is not soluble. Pb sitting with SO4, not soluble. Ag sitting with SO4 is not soluble, but all other are soluble. You got it? So like that. That's how we read this table, yeah? So there will be definitely some question in exam and in homework. So let's go to the next one. Now this is the table for the insoluble salt, insoluble. So if you look here, carbonate. So there is a CO3, and let's write this. This table is for insoluble, not soluble. Soluble, we already finished it, yeah? So let's write the carbonate here. So I'm writing carbonate here. So I'm going to write something here. So maybe I write sodium here. You see sodium and carbonate sitting together. I'm even not concerned with the molecular formula yet. Actually, this is Na2CO3. So let's look carbonate sitting with Na. So look here. So what they are saying is sodium, lithium, sodium, potassium, rubidium, francium, sitting with all these elements, all these ion is soluble. Lithium carbonate is soluble, sodium carbonate is soluble, potassium carbonate is soluble, RB carbonate is soluble, francium carbonate is soluble. Here is an exception. Everybody got that? So how about the this one? So I'm going to write this one, calcium carbonate. So calcium carbonate, will it be soluble or not soluble? Let's look here. So carbonate is right here. We don't have exception here. We don't have exception here, meaning that calcium carbonate is insoluble compound. Everybody got that? So anything ammonium carbonate soluble, ammonium phosphate soluble, ammonium oxalate soluble, ammonium chromate soluble, everything sitting with ammonium and these elements and BAS, these compounds are soluble, all other things are insoluble. So let's write another one. So with something sitting with phosphate, PO4. Let's write Cu in front of this one, CuPO4. So Cu and PO4 are sitting there. Would it be soluble or not soluble? So PO4, that is your Cu here. So CuPO4 definitely is insoluble. Everybody got that? That's no exception. CuPO4 is insoluble. Got it? So this is one way of looking things. And if you look another one, most metal hydroxide and oxides are insoluble. So let's write oxide and hydroxide of metal. So I'm going to write oxide of copper. So this is CuO, copper oxide. I write CuO. Would it be soluble or insoluble? So copper is metal oxide. So copper oxide, it should be insoluble. This is insoluble compound. So which kind of the oxide and hydroxide is soluble is this one? Yeah. So look here. Alkali metal hydroxide are soluble, meaning that alkali means those LiNaKBr, those are alkali. So NaOH. So this is exception to insolubility. Look here, alkali metal hydroxide. So LiOH, NaOH, KOH, RbOH, FrOH, all those are soluble here. Everybody got that? So other kind of, so if you write something like this, FeOH2, so this is going to be insoluble. So this is not alkali metal. Got it? So this is one, these are the table, and that's how you are going to read this table. So and BaOH2 is also soluble. BaOH2 is soluble, SrOH2 is soluble. Yeah. So I put this table here. So I showed this table in last class. It's very easy. So if you may want to use this table, this is the most easiest table I found. Yeah. So basically, you just pick one compound from here. So let's say Ba sitting with OH. Would it be soluble or not soluble? So Ba here and OH here. So go down from Ba to here and from OH to here. So BaOH is definitely soluble. So that's a green button there. So BaOH2. So this is definitely soluble. So this is the most easiest table to use. When you use this table, you can easily know how to use the another table. Everybody got that? So we are going to use this table later to identify whether some compound are soluble or not soluble when we do the reaction. Any question? Good. So there are some reactions in water. So I'm going to talk about this reaction. So first reaction is exchange reaction. So let's talk about this exchange reaction here. So I have here, so let's say you have one compound like AB. This is one compound AB, and there is another compound CD. So you mix these two compounds in water, and how do they react? So this B is going to sit in place of D, and D is going to sit in place of B. So this is exchange, yeah, it's just changing the friend. So they are changing the friend. So that A becomes A sit with D like this, AD, and C and B sit together, plus C and B. You see that? So this they exchange the partner. So this is one kind of the reaction called exchange reaction. Now let's write one real example here. So the example here is NaCl. I have a sodium chloride and I have silver nitrate. So I throw these two compound in water, right? So these are the reaction in water. So the first is always plus, second is always minus. First is plus, second is minus. These are ionic compound. Just change the friend. So Na is the first, NO3 is the second. So put this first guy with the second guy here. So the Na, NO3, and then this first is Az, and then this second goes here. So always we need to put the first in first, first in first, and the second in second, just like that. Everybody got that? So meaning that plus, we always write first, and then minus we write in the second. Everybody got that? So while you are exchanging these ions, the plus guy should be written first, the plus guy should be written first, and this Cl was sitting here with Na. Now this Cl is going to sit with the Az here and behind, and this NO3 sitting with Az now is sitting with the Na and sit just behind the Na. Any question? So this kind of reaction is called exchange reaction. So if you, since this reaction are done in water, so sodium chloride completely dissolved in water. So we write AQ. So AgNO3 is also completely dissolved in water, so that we write AQ. So sodium nitrate completely dissolved in water, we write Q. But AgCl does not dissolve in water. Now you can go back here and look that table whether AgCl dissolve and does not dissolve. Where is Az? So Az is right here. Now where is Cl? Cl is here. Let's go and find AgCl. So I go here and from here. So AgCl is insoluble. Everybody got that? So that is solid, or you can write the precipitate. So this guy is solid. Sometimes they write the PPT. So this guy does not dissolve in water. Therefore, we need that star. Got it? Like that. Good. So there are some reaction in another slide I am showing here. So let's practice couple of problem here. So I'm going to write the third problem here. And there are many problems you can practice yourself in home. So so here is a problem, lead PbNO3. So PbNO3 PbNO3 2, and then so this is lead nitrate, and we are going to react with ammonium sulfide, NH4 ammonium sulfide, and we get basically this is the first guy, and this is going to sit with the second guy here from another compound. Everybody got that? So how much is charge here? So 2 is here. So this 2 is coming from the head of this guy. So you could write the +2 here. For easy, yeah? And then there is nothing, 1 here. So this 1 is coming from the head of this guy. So there is -1 with that nitrate. Now, this 2 is coming from the head of this guy. So that's -2. And there is nothing here. There's a 1 here. So that must be coming from the head of this guy. So ammonium is +1, sulfur is -2, nitrate is -1, lead is +2 charge in this compound. Everybody got that? Any question? Good. So like that. Now let's exchange the position. So Pb should be sitting with the S. So PbS. So basically this is also 2. This is also -2. So 2 comes here, 2 comes here. So we don't write the 2. I already explained this kind of phenomena to you, like the PbS. Now this is the first guy, and this first guy is going to sit with this one, that is NH4 NO3, like that. Yeah. So if you look here, NH4 is +1, NO3 is -1. So 1 comes here, 1 comes here. So we don't write that 1 in 1. Everybody got that? So now let's look here. So this is soluble in, I'm just throwing this 2 compound in water, and this forms, these compounds are formed. So is it soluble or not soluble? Let's look the PbS. So is it soluble or not soluble? So Pb. So this is Pb here. This is S here. So let's find that PbS, right? This box. That's an insoluble compound, right? So this is a precipitate. So you can write solid or precipitate. But this guy, ammonium nitrate, you can find ammonium nitrate here. So that's a ammonium, and right here is a nitrate. So go to down here and come to nitrate. So this box is green box. It's soluble, right? So ammonium nitrate is, we are going to write this as a AQ. So all other are AQ. So everybody got that? So reactant, definitely this is also AQ. This is because we are doing in the reaction in the water. So definitely this is dissolving in water. This is dissolving in water. but when they react, so we get some solid precipitate there, and another compound here is dissolving in water that we can see with our eyes. Everyone got that? Like that. So let's write one more reaction here, and then we can move in another slide. So I'm going to write this one, FeCl3. I dissolve this in water, AQ, and then I react that with sodium hydroxide. This is also dissolved in water, AQ. So what happens? So let's do reaction. So basically, so this is OH ion, this is Na ion. So OH is, so there is 1. That means OH is -1. There is 1. So OH is -1. There is 1. So Na is also +1 like that. So here, this 3 is coming from the head of this guy. So this is +3. There is nothing. There is 1 here. So that 1 is coming from the head of this guy. So that's how we find the charge in the ions. Make sense? So when I throw those compounds in water, they dissolve and give the ions like that. Now, let's write the reaction. So Fe is going to sit with OH. So Fe is going to sit with OH. And I told you Fe is 3. So if 3 is here, that is going to go down and sit here like that. So there are OH3. So one Fe can hold 3 OH like that. But OH is -1 here. So this one comes here. We don't have to write that one like that. And another one is, so Fe and OH. I just write. Now I'm going to write Na sitting with Cl. So Na sitting with Cl. If you look here, Na is 1, Cl is also 1. So this is 1 here, this is -1 here. If 1 comes here, we don't have to write that NaCl, just like that. Everyone got that? That's how we write the ionic reaction. So we will be doing this in the lab 5 in Chem 106 too. Any question here? Pretty easy. Now let's look which compound is soluble. These both are soluble. NaCl and FeOH3, are they soluble or not soluble? Let's look those. NaCl. So here is a Na, here is Cl. So NaCl here is clearly the soluble, green button here. So FeOH3. Now let's look FeOH3. Fe here, where is OH? OH here. So let's go here and find that Fe and look here. So this button here from Fe down and OH here, that's insoluble. Insoluble here. Everyone got that? So FeOH3 is a precipitate here. So we write solid, or you can write the PPT, and this guy is. So hopefully you know how to practice this reaction now. Everyone got that? Good. So I'm not going to talk all the reaction here. Now let's look some definition in another slide. So these are the ionic reaction, right? So if we write any reaction, let's say AgNO3 reacting with, so this is AQ, dissolved in water, and NaCl, this also dissolved in water. So dissolved in water, AQ means it dissolves in water, and I am throwing this water together, and I'm just exchanging. So Ag and Cl are going to sit together, and Na and NO3 are going to sit together like that. Na and NO3 are going to sit together. If you want to find the charge here, Ag, so NO3 is one chunk here. So this is called polyatomic ion, which is -1. If you look the polyatomic ion chart, and there is 1 here, so Ag must be +1. There is 1 here, NO3 must be -1. And here is 1, here is 1, Na is +1, so Cl must be -1. So -1 and +1, 1 comes down here. So again, Ag is +1 there, Cl is -1 here, so 1 comes here, 1 comes here, so AgCl is good. So Na is +1 and NO3 is -1, so 1 comes here, 1 comes here, so we don't have to write those. Got it? It's just like that. So we just pull forward to put, or we take from put to head to find the charge. So now let's look AgCl. If AgCl is a soluble or not soluble, so you can find Ag here, and Cl here. So let's go and find AgCl. So clearly there is a red button here, so it's insoluble in water. Everyone got that? So that's solid. So this is solid, and all NaNO3. Is NaNO3 soluble or not soluble? So let's find that one. NaNO3. So Na is right to here, NO3 is right here. So NaNO3 is a green button here. So that's soluble. Yeah. So this is soluble. So we write AQ. So if you write this like this way, if you write this equation like this way, full this kind of writing is called molecular equation. Everybody got that? Complete equation or molecular equation. See? So we write everything like that, and this kind of writing is called the molecular equation. Good. Now you can break them. Let's break them. So AG is +1. AG is +1. I told you 1 coming here, meaning that AG is +1. So you can write just plus there. And then you can write NO3. NO3. So 1 is here. That means NO3 is -1. So we don't write 1 there. So minus is enough there. So now let's look here. Na is here. So Na, the foot of Cl is 1. So that means +1 with the sodium there. So we don't write 1. So I write plus. And then chlorine here. So foot of Na has 1. So that chlorine must be 1 there. So I don't write minus there. Now I'm going to write the right side here. So AgCl, it's solid. We cannot break it into 2. How I am breaking the previous one, I cannot break it because it is solid and it cannot be broken by water. Everybody got that? So I cannot break this one. So AgCl. So I don't break this one. It's solid. Now Na and NO3. So it's soluble. I write AQ here. So Na, this is +1, and NO3 is a -1. So I should break that one. So whatever AQ that dissolve in water, I can break them. And Ag is in water. So I write AQ. This is in also water. AQ. This is in water. AQ. This is in water. AQ. This is not soluble. So I write solid. Na is in AQ, and this is AQ. If you write like this way, it is called a full ionic equation. Everybody got that? If you break all those soluble compounds into ions and write AQ, 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 then this kind of writing is called full ionic equation. Everybody got that? So now, from this full ionic equation, what you can do is, so molecular one, now full ionic equation. Now from this full ionic equation, only find that what is solid. So solid is this one, right? AgCl is solid. So I just write that solid here, not other thing. AgCl solid. And this is coming from Ag plus. So Ag is coming from Ag plus and this Cl minus. So this is AQ. Look here. This is AQ. Cl is here. This is also AQ. And Ag and Cl are combining like that. And this is called net ionic equation. Net ionic equation. If you write like this way, it is called net ionic equation. You got it? So you will be practicing a lot of this in lab number 5. Yeah, the only solid part. So what is giving the solid, and that's solid. When we write this way, this is called net ionic equation. So what I didn't write here, I didn't write here Na and NO3. So I didn't write Na and NO3. So those Na and NO3 that I didn't include here is called spectator ion. So they do nothing and they just floating around in water. Everybody got that? So Na and NO3, which I didn't include here. So they are called Na plus and NO3 minus, which are here. So this is Na and NO3 that I didn't include in my net ionic equation. They are called spectator ion. Spectator ion. So spectator means like they are just floating around there and not really reacting, not coming in, not sitting together. Everybody got that? So like that. Good. Alrighty. Now let's practice one more and then we go to the next topic. So I'm going to something that I don't include in net ionic equation are called spectator ion. So let's practice one more equation here and then probably you will understand more. PbNO3 2, that's AQ. So it is dissolved in water, and then potassium iodide. So this is also dissolved in water and they react. When I mix them together, they react, and this first guy is going to sit with this guy, and this first guy is going to sit with this second guy there, right? Now, how much charge with the PB here? So in the foot of NO3 here, there is 2. So this guy must have +2 charge. And at the foot of PB here, there is nothing. That means there is 1. So this NO3 must have -1 charge there. Everyone got that? Or you can look the polyatomic ion chart. So it's clearly written there. Now let's look here. At the foot of potassium here, there is 1. So I is -1. And at the foot of I there is nothing. There's a 1. So that's a +1. So it's easy to write the charge with those spaces, just looking at the foot of those spaces. Everyone got that? Good. Alrighty. So put this guy with I here. So that is PBI. So PB has +2 in the head here. I has -1 in the head here. So this one comes here. So 1, I don't write. So this 2 comes and sit with at the foot of this I. So I just write like that way. So PBI2. Everyone got that? How I'm just building the equation? Yeah. Now like that. So another one is potassium is going to sit with the NO3. So A plus, this is +1 here, and NO3 is -1 there. NO3 is -1 there. So 1 comes here, 1 comes here. So I don't have to write the 1. So KNO3 basically like that. Now your job is to identify, is it soluble or not soluble? So this I'm throwing in water. So they are definitely soluble in water. Now, is this soluble in water? This is soluble in water? I don't know. So let's look at table and find PBI2. So PB is, where is the PB? Right here is the PB and I is here. So let's go here and find this PB. PBI2 is insoluble. Have you got that? So this is insoluble. So you can write a solid or a precipitate, whatever, or insoluble, what you want to write. Yeah. So, and this, how about this KNO3? So let's look the KNO3. So K is here, the NO3 is here. So KNO3. So right here, that's soluble. So this is aqueous. So this guy is aqueous. Any question here? Easy, right? Now, just write. So this is a molecular equation. So now let's write the net ionic equation. So I just take that solid PBI2 and write here. So PBI2. So that solid I pick, and these are coming from the oh no. So I'm going to maybe I write the somewhere here. So let's write the net ionic equation PBI2, and this is solid, and this is coming from PB there, and where is I? So I is here. So I is here. So PB was in +2 state because there is 2. So I already write the +2 here. So PB and I is -1 here, and PBI2 like that. So if you write like this way, so this is AQ, this is AQ. So this is called net ionic equation. Everyone got that? So that's how we write the net ionic equation. Yes. I didn't talk about the balancing the equation, but we need to balance the equation by putting the coefficient at the front. Have you got that? Otherwise, charge is not balanced, atoms are not balanced. We need to balance those. Yeah. So this is called the net ionic equation. Now, what is the spectator ion here? So I didn't write any K and any NO3 here in the net ionic equation. So K plus and NO3 minus are the spectator ion now. Got it? So whatever the solid forms, you identify the solid first, right? And then just take that solid and write the related ions, and that is called net ionic equation. And whatever is not in that ionic net ionic equation, and they are spectator ion. Yeah. So you could write the full ionic form here also, like the total ionic form. So total ionic form is much easier to write. So you could write the total ionic form is PB 2 plus and then NO 3 minus, then A plus, this first plus, and the second is I minus, and then you just write the arrow here, PBI2 is just the solid there. So we cannot break this one, and you write the K plus and plus NO3 minus. So this is AQ, and this is AQ, this is AQ, this is AQ, this is AQ, this is AQ. Everybody got that? So that's a total ionic equation. Yeah. molecular equation, total ionic equation, net ionic equation, and spectator ions. So spectator ion don't appear in this net ionic equation. Have you got that? So maybe you practice a couple of times and then should be good. So that's how we identify whether they are soluble, not soluble, which are ionic, which are soluble, which are not soluble, and which are spectator ions and which are not spectator ions. So let's practice more. And we will be doing a lot of practice in Chem 106 in lab number 5. So now I'm going to talk about the another kind of the reaction, and this is called acid-base reaction. So we just finished those ionic equation in ionic reaction in water. Now exchange reaction in water. Now we talk about the acid base reaction, acid base. So acid base. So there are a couple of definitions of acid and base. So what is acid? So acid is something you throw in water and it gives a H plus. Yeah, H plus. So that is called acid. So you have a compound, throw in water, and that compound break to give H plus, and that is called acid. Everybody got that? So like this one. So let's say I have a HCl and I throw it in water and it gives H plus and Cl minus. You see that? It gives the HCl, I put it in water and it breaks to give the H plus, and therefore HCl is acid. Everybody got that? So anything, just throw in water and that breaks to give H plus in water, and that is called acid. And it gives the sour taste, so therefore it is called acid. Yeah. So now what is the base? So throw anything in the water and that gives OH. So I'm going to write base here. So base. So throw anything in water and it gives base. So for example, you have NaOH. When I throw this in water, it is going to break like this, Na plus and OH minus, and so in water. So AQ means in water, right? And I throw this compound in water, it gives me OH minus. So that means NaOH is a base. Easy? So this is called the Arrhenius definition of acid and base. Yeah. So the guy named Arrhenius, a very famous chemist, give the definition of acid and base like that way. Throw anything in water and that breaks into to give H plus, that compound is called acid. Throw anything in water that breaks to give OH ion in water, that is called base. If you got that? So like that. Now there is another definition given by, so this definition is given by Arrhenius. Now I'm going to write the another definition given by Bronsted, B-R-O-N-S-T-E-D, Bronsted and L-O-W-R-Y, Lowry. So these two guys give the definition of acid and base the another way. So let's write that. So they said, this is a compound here, HCl, and this is another compound here, water. So one guy gives H plus, another guy picks that H plus. Make sense? So this is a guy that gives H plus, gives H plus. Make sense? And this guy picks that H plus. So that which picks that H plus is called base, and the guy which gives H plus is called acid. Everybody got that? Something that gives, so you mix these two things. So one guy gives H plus and another guy picks that H plus. Everybody got that? So that which picks the H plus is called base, which gives the H plus is called the acid. Yeah. So like this. So let's write this one. And so this is going to give this H to this guy. So this becomes, this is H2O. Now if H is going to combine with this one, that becomes H3O. See that H2 is already there. H comes and sit with H2O and it becomes H3O plus. And there is a Cl minus here. Cl minus here. You see? So HCl gives this H to this guy. So this gives H plus to this one. So this is acid. This picks the H given by this one. So this is base. Look here, H2O is neither acid nor base, right? But here, water is also behaving as base. If there is a strong acid like this, water behave as a base because it picks that H plus given by the acid. Everyone got that? So here water is behaving as base. Yeah. Did I make it clear? So somebody who is giving the H plus is called acid, and somebody who is there to pick that H plus is called the base. Here water is the base. But normally water is not base, it's neutral, right? Water is neither base nor acid, but in presence of strong acid, water behaves as a base. Yeah, good. So, so basically we are doing this in water. So if you see something like this, sometimes they write like this way, or sometimes they might write just the plus like this, yeah? So this one and this one in water is the same thing. Everyone got that? So this is called proton, proton, proton. So this H plus given by this, sometimes we write, oh, okay, H plus is there in water. Sometimes we write, okay, that H plus is picked by water and become H3O. So if you are writing this way or this way, it's the same thing. H plus or H3O plus is the same thing, yeah? So H3O plus is also the acid. Good. In water. Now, let's write another one here. So this is acid, this is base. So I'm going to write one more here. So let's write one reaction. So this is H plus. H plus means somebody give the H plus there. So this is already acid there. Now there is a NH3. So this is ammonia. So this is going to pick the this H plus. So that becomes already there are NH3. Now this comes and sit with this one and it becomes a NH4 plus like that. So plus comes like that way. So look here. So somebody give H plus here. So this is acid. It's a give, right? So that's acid. And this H plus is picked by NH3 here. So this is base. This is base. Everybody got that? So instead of writing that, you could also write that instead of just writing H, you could write HCl also. And you could write NH4Cl like that way. The same thing, yeah? So if HCl is meaning that this H is coming from somebody. So maybe HBr, HCl, HNO3, I don't know which acid. You could write just H there. So this is acid and this is base. So somebody give this H plus. So there is an acid, it itself is an acid, and NH3 pick this H plus and this is base. And got it? So anything that gives acid, anything that gives H plus is acid, anything that picks H plus is base. Make sense? Good. So like that. So we are all talking about the reaction in water here, right? So let's see one table here. So look here. So this is a chloride ion, right? Cl minus. So if you combine that Cl with H, it becomes HCl. So this is hydrochloric acid. So combine ClO with H and HClO. Look here. So I just put HClO together. So that's hypochlorite ion. So hypochlorous acid, something like that, HClO. And ClO2, this is called chlorite ion. Put H with HClO to here and it becomes HClO2. So it is a chlorous acid. So we don't use that many acid in laboratory. So this is very important acid here, HCl. Most of the time we use this H2SO4 and HNO3. So HNO3, H2SO4, and HCl. So these three acids we use most of the time. So look here, HNO3. So HNO3, so H2SO4, and HCl. So these three type of the acid we use most of the time in laboratory. Yeah. So if you throw this guy in water, it is going to give H plus in water. So this is acid. If you throw this guy in water, it's going to give 2 H plus there, so because there are 2 H's, right? So this is also acid. And if you throw it in water, it's going to give H plus in water. So these all are acid there. Everybody got that? So would it be acid or base? CH4, would it be acid or base? You may think that, oh, this is acid because it gives H. No, it doesn't give acid. So it doesn't give H, yeah? Although this compound has H, so throw in water, that doesn't give H plus in water. So that's neither acid nor base, yeah? So, so which are acid? So these compounds are acid. HCl, HClO. So there is clearly not CH4, right? There is no CH4. Make sense? So sometimes, oh, there is a compound. So this must be acid. You might know there is H, so it gives H to the water, so it must be acid. It doesn't dissolve in water and gives H plus. It doesn't ionize. Yeah, so this kind of compound are not acid. Although they have a lot of hydrogen. Everyone got that? So like that. So already, so now let's talk about acid and base strength. So you already know about this acid and base strength. So let's say you have HCl here. You have 100. You throw the 100 molecules of HCl in water, and all 100 molecules break into H plus and Cl minus. All 100 H and 100 Cl. You got right. So this kind of acid are called strong acid. Have you got that? So already we talk about the strong electrolyte and weak electrolyte, right? So if all the molecules break and give their product, they are called the strong electrolyte, or this is called strong acid. So hydrochloric acid is strong acid. Why? If you throw 100 molecule of water in 100 molecule of HCl in water, all 100 molecule of water HCl break to give H plus and Cl minus, like that. So look here. So like this. So they are called strong acid. Everyone got that? Everything breaks, right? Now, how about the, so all this acid I showed you previously, HCl, HNO3, H2SO4, throw these things in water, no matter how much you throw in water, they just break to give H plus and Cl minus, H plus and NO3 minus, H and SO4 minus, like that way. So they are called strong acid, yeah? So put a little bit in hand, and say just cut your hand or cloth, strong acid. Everybody got that? So like this. So with 100 molecule, all 100 molecule break. So to give S plus and Cl minus. How about the strong bases? So strong bases, again same thing. So they have OH, so they give OH in water. So put 100 molecules in water, all 100 molecules of that NaOH are going to ionize to give Na plus and OH minus, like this way. So 100, so 100, 100. You see that? So all the molecules just dissociate to give the ions in water. So you can write the EQ here in water. So this is also in water. This is also in water. So this kind of compound are called strong acid and strong bases. So this anyways gives the OH in water. So this is a base. So if you put 100 molecules in water, 100 out of 100 molecule break to give Na and OH. So this is called strong base. Have you got that? Just like that. So now let's talk about the weak acid and weak base. The weak acid. Now I'm going to talk about the weak acid. Weak acid. So weak electrolyte. You already know about this weak electrolyte. Let's talk about this one. CS3COOH. So this is a vinegar acetic acid we talk in the weak electrolyte, right? So if you put this 100 molecules of acetic acid, only one molecule break to give CS3COO minus and H plus. So it breaks right here, and this part is minus, and this H is plus. So out of this 100 particle, only one particle break to give this product. Everybody got that? So this is weak electrolyte. Yeah, you throw 100 gram there in water, only 1 gram break to give H plus and CS3CO minus. All 99 gram is still in this form, right? So out of 100, so you start with 100. So you have only one product, and out of that now 100, you are still left with 99 of these molecules are just not dissociated. So this kind of acid are called weak electrolyte, right? You got it? So just like how we discussed in the last class, what is the weak electrolyte? Just like that, yeah? Good. So weak acid. Now let's talk about the weak base. So weak base is same. So take one base. So I'm going to write one base here. So that base is ammonium hydroxide, NH4OH. So like that, right? So NH4. So if you put 100 molecule of NH4OH in water, so this is going to break like this: NH4, NH4 plus, and OH minus. So out of, I don't know how many molecule of break here. So maybe if you start with 100 molecule of NH4OH, maybe 5 molecule break and give 5 particle of this, 5 particle of this, and still 95 particle of this is left behind. So it doesn't break well. Make sense? So you started with the 100 particle of 100 molecule of NH4OH, you throw it in water, and you did after a while, you come and you started to count how many NH4OH are left behind. Still 95 molecule out of 100 were still in the form of NH4OH, then they didn't break, right? So this kind of base is called a weak base. Everybody got that? It's easy, right? So if 100 out of 100 pass, that's kind of the strong base. If only 95, if only 5 pass out of 100, that's just the weak class, right? Like the weak base. Everybody got that? So good. Like that, and strong acid and weak acid. So we talk this one, strong base and weak base. We talk this one. Now I'm going to talk about the polyprotic acid. Poly means many. Protic acid. Polyprotic acid. Poly means many. Many. Protic means H plus. Many H plus acid. So one acid has many H plus. So if you throw the acid in water, one molecule of that acid gives many protons, many H plus in the water. Make sense? So that this kind of acid are called polyprotic acid. Now let's look here, HCl. So if you throw this guy in water, it has one H, so it gives us one H plus and one Cl minus. So this is not polyprotic acid, it's a monoprotic acid, only one. So this acid is monoprotic acid. Mono means one proton. So H plus is called proton, yeah? Sometimes H plus is called proton. Yeah? Everybody got that? So it's HCl is a monoprotic acid. How about HNO3? HNO3. So throw this into water, it gives only one H plus and one NO3 minus. So this guy is a monoprotic acid. It gives only one H plus, right? Everybody got that? So let's look another one, diprotic acid. So let's look at diprotic acid. So H2SO4. So throw this compound in water and it gives this 2 hydrogen like that, 2H plus and SO4. So you can get this charge SO4. Since 2 is here, this 2 is coming from the head of this SO4. So that is -2. Look here, how many proton it gives? 2 proton it gives, right? So this kind of acid, H2SO4, is called diprotic acid. Di means 2. It can give 2 proton in water. Everybody got that? Any question? Good. So H2SO4 is a diprotic acid. How about H2CO3? H2CO3. So this has also, if you put this carbonic acid, although this is a weak acid, so if you put this guy in water, so it gives also 2 protons there, 2H plus and CO3 minus, like that, -2. So this is also diprotic acid. Di means it can give 2 protons if you throw it into water. Yeah, good. So how about triprotic acid? So it looks like there are some triprotic acid also. So triprotic acid. So here is a famous example, S3PO4. So if you throw this guy phosphoric acid in water, it can give 3 proton from there, 3H plus and PO4 minus. So look here, 3 coming from the head of this PO4. So this guy should be -3 here. Yeah, so this 3 is coming from the head of this one. So we write like that way. So S3PO4 is triprotic acid. It gives 3 proton in water. Yeah. Everybody got that? So I'm going to write one here, and so I think fine. So let's write the citric acid. I'm going to write one example here and show you why all hydrogen cannot be. So let's write S3 C6 H5O7. So if you count the hydrogen here, there is 3 hydrogen, there are 5 hydrogen. So you might think that, oh, there are 8 hydrogen plus. So this is a 8 protic acid. You might think that way, right? But it doesn't work that way here. So this compound actually is called citric acid. And citric acid have how many carbon? 1, 2, 3, 4, whatever. So if you write the structure of this guy, looks like this. So it's a long structure here. So I'm going to write here. So like this. So and I will tell you whatever. COOH here and COOH here. So I'm not even considering where I'm putting. So in this kind of the compound, so if you look, if there are something like H sitting with this double O, then you can say that only this is a hydrogen is ionized. So this guy, this hydrogen are not ionized. Only those hydrogens sitting with double O, COOH. So this group double O here, here double O here. So this kind of hydrogen only can go out from their H plus in water. Make sense? So this hydrogen cannot come up from that compound. So look here, there is a compound here. So I just want to show you. It's a little bit hard to draw there. So strong acid. So look this compound here. So if you here, look here, this guy here, this is a citric acid. This compound structure has like this one. This is C here, COOS. So this guy here, so look here. So this guy here, this H can come out from there if I put this compound in water. And there is COOS. So from this group, this guy can come out from this compound in an H plus in water. And same here. So if you look here, this here, and this guy, this H also can come out as H plus in water, H plus in water. But all other hydrogen, this hydrogen is only with OH, so that cannot come out. So there are two hydrogen here, they are not showing, they cannot come out in water. There are two hydrogen here, they cannot come out in water. So we need to look this, if you see something like this, like the big organic acid, we need to look the COOH, and how many COOS there, that many H can come out from there. Have you got that? So this is a little bit difficult, so you will study in future. So here also I'm showing this can come out, this can come out, and this can come out. So this is a triprotic acid. So like that, and all right. Got it? So all hydrogen that are in a compound cannot come out as H plus in water. So we cannot say they are acid. So if that is the case, all compound would be acid, right? So you write a compound like, let's say C2H6, something like this. Then you could say, oh, it's an acid because there is hydrogen. But if you put this compound in water, it cannot give H to the water, H plus to the water. So this is not the acid. Everybody got that? So you put a compound having H, and that H can be given out to the water as H plus, and only that compound is acid. Yeah. If there is a H, and that should not always be the acid. So like that. Now go down here. Now acid-base neutralization reactions. So if you react the acid with the base and you produce water and salt, that is called neutralization reaction. So HCl is acid, right? In water, again, we are talking in water. I put some HCl in water, AQ, and I am putting some base in water. So this is also AQ. This is base. Why? Because it can give OH minus in water. This is acid. Why? Because it can give H plus in water, right? That's the definition of acid and base. Everybody got that? Now what happened here is this first guy is going to sit with the second guy here, and this first guy is going to sit with this one. So H and OH are going to sit together to give. You can write HOH or you can write H2O like that, and you can write Na and Cl together and NaCl. So again, this is water is liquid, NaCl is dissolved in water. Look here. So this is a base because it has OH. This is acid because it has H plus or H, and I react acid and base in water, and I produce from those water and salt. So NaCl is a salt, right? So if you do something like these reactions, they are called acid-base reactions. You mix the acid and base together in water, and you produce salt and water. Everyone that? So these are called neutralization reaction or acid-base reaction. Why it is called neutralization reaction? This is not acid, not base. This is not acid, not base. So from acid and base, we got neither acid nor base, neither acid nor base. So we neutralize acid and base together, right? So it is called neutralization reaction. You got it? Have you got that? So we just combine first with second and first with second of this way, and then this is called neutralization reaction. Sometimes it's easy to write just, don't write this one, don't write this one, and we don't write this one. We just write this, just this one. So H plus and OH minus. So acid and base combine to give water, and this is also neutralization reaction, yeah? Because H plus is acid, OH minus is base. So we are just combining H plus and OH minus, and that's called to give water, and it's called the neutralization reaction, yeah? So sometimes you see something like this, sometimes they write, okay, we write HCl and NaOH or KOH, whatever, and they write Na and Cl sitting together here, something like this. So either way is fine when you write the neutralization reaction. So let's write another one. So HBr. So this is also acid because the H sitting with another Br there. So if I throw it in water, it gives H plus, and I can write that I can react this with the potassium hydroxide. This is metal. This metal sitting with OH. Now I'm doing this reaction in water, so I need to write aqueous. So this first guy is going to sit with the second guy, that is H2O. This second guy is going to sit with this first guy, so that is KBr, like that. So this is AQ, this is liquid water. So this is salt, this is water, this is base, this is acid. So I combine acid and base to give salt and water, right? So this is called neutralization reaction. Everyone got that? So like that. Now, now I'm going to write one with the weak acid with this weak acid strong base kind of the reaction. So I told you this guy CS3. So I could write a little bit simpler. So whatever I have here, I'm going to write that one here. So CS3, CH2, COOH. So I can write this one, but you can also write simple compound like this, CS3COOH, yeah? So this is a vinegar, acetic acid. So I write a little bit longer compound here in my note. So I throw this in water and I put some NaOH in water. So this has H. This H is not acidic. This H is not acidic. Only this guy is acidic. I told you, right? If you see COOH and that H is acidic, so that can break and go out in water. Other this H and this H cannot be broken there. So this is in, I throw it in water, together, and the reaction is like this. So this guy break here, and then this is H plus, and this guy break here, this and this going to sit together, CH, H2O. So this is OH and H, H2, H2O. So this is water, and Na and this guy are going to sit together. So that is CS3, CH2, COO. So that was a minus side here, and this is a plus side here. So Na, like this. So this is minus, this is plus, CS3, CS2, COO, Na. So this is salt, this is water. Now this is also kind of neutralization reaction. Have you got that? Because we are reacting, that is a weak electrolyte. This is a weak acid with a very strong base, and we got this compound. You got it? So that's how we write. We need to practice a lot, right? General chemistry is 2 months, right? We need to practice 2 times, and so you can try this way. So how about, so there is no acid and there is, so if you see something like this, NaOH and HCl, you can easily say, oh, this guy has a OH, so this is acid, this is base. This guy has a H plus H and it is acid. But how about some oxide? Let's say CO2 or Na2O. So is this an acidic oxide or is this is an acidic oxide? Meaning that, let's say this is the oxide I have, I want to throw it in water. Would my water be sour or it would be like a bitter? If it is a bitter, it is a basic. If it is a sour, it is a acidic, right? So it's easy way to find out is, so go to the periodic table, and so I'm going to show you periodic table here. So this periodic table we have in our book. So look here, all these blue elements are metal, right? So that guy is sitting with O. So let's pick any of these blue elements. So I pick one blue element from anywhere. So I want to pick from Na. Let's say I pick there. So that is I treat that with a NaO. So basically I need to write Na2O. So this compound is definitely a basic oxide. Everybody got that? Any metal sitting with the oxygen, that compound is definitely the basic oxide. So if I throw that in water, it is going to react and give me OH minus. Yeah. So how to find whether some oxide is basic or not? Anything, take any of these blue element and put O with them, and that compound becomes the basic oxide. Everybody got that? So I'm going to take, let's say, iron here, Fe. So I'm going to take iron, Fe, and then I'm going to put that with O. So if I write the real correct compound, this becomes Fe2O3. Fe is sitting with O. Is this an acidic oxide or basic oxide? Fe is the blue element here, right? So metal. So metal sitting with the oxygen is definitely a basic oxide. Everybody got that? So any of those blue elements sitting with the oxygen is basic oxide. Yeah. So you need to find. So I will give like a 5 oxide in exam, and I will tell you which oxide are acidic and which oxide are basic, right? And you need to identify acidic oxide and basic oxide. Got it? Now we are done with the basic oxide. So Na2O is basic oxide, right? So Fe2O3, Na2O, right? Anything you like. Na2O, copper oxide, any blue, and put that together with oxygen, and that becomes immediately the basic oxide. Meaning that if I put that in water, it gives it behaves as a base. Yeah. Good. Now how about the acidic oxide? Take any this orange element and put that with the oxygen. So I'm going to take N and I put that with the oxygen, NO. So it's an acidic oxide. If I throw this in water, the water becomes sour in taste. Yeah. So this is the acidic oxide. Everybody got that? So pick another one. So there is a carbon here. So this is carbon here. So carbon is also non-metal. So carbon put with the oxygen, CO2. So this is also the acidic oxide. Easy? Easy to find? So let's find the N2O5. So there are many oxide of nitrogen, N2O5. Will it be acidic or basic? So nitrogen is that orange element sitting with oxygen. So this oxide, if I throw in water, it gives sour taste. Yeah. So this is the acidic oxide. Everybody got that? Easy, right? Good, like that way. So good. So, so these are acidic and basic oxide. How about this guy? So these are some of the famous oxide. I'm picking it here. So let's pick one compound here, SO2 and SO3. So let's look whether these are acidic or basic. Look here, S, where is S? S is this orange element sitting with oxygen. So this, if I throw this in water, it gives sulfuric acid, something like that. Yeah. So this is acidic oxide, and this guy SO3. S is right here. That's also orange element. That's non-metal, right? Non-metal oxide. That's also is acidic. How about this P? So let's say I write the P2O5 here. Where is P? So look here, P. That's also orange. So P2O5 should be acidic oxide. So if I throw that in water, it gives phosphoric acid or something like that. Easy to identify? This periodic table is a lot, yeah? So when you know how to read this periodic table, it's easy to solve most of the problem, yeah? Everybody got that? Like this. Good. So I have put some reaction and how to identify. You can just read those there. Now we will practice some question in next class before first exam, and that will also help you. So, now I'm going to talk about the third kind of the reaction. That's called the oxidation reduction reaction or redox reaction. Redox reaction or oxidation reduction reaction. Sometimes they call oxidation reduction reaction. So oxidation means it's throw electron is oxidation, pick electron is reduction. Everybody got that? If somebody pick the electron, this is called reduction. If throw oxidation is called oxidation. Look here, most of these blue element throw the electron out. So they most of the time they oxidize. and these orange element try to pick this electron, so they most of the time they become reduced. Make sense? So these blue element most of the time throw electron out. So that's called oxidation. So I'm going to write the oxidation here, and so I just pick one those blue elements. So let's say I pick the lithium. So lithium is in group 1, right? So it has 1 electron in outermost orbit like this. I already taught you in the chapter 2, right? So lithium is right here, is in the group 1. So in outermost orbit of this lithium, there is 1 electron, and if it reacts, it is going to throw this electron out like this way, Li, and electron like that. That electron is thrown out, and we write plus here. So lithium is oxidized here. So this kind of reaction is called oxidation reaction. Everybody got that? So all those blue elements in the periodic table try to throw out the electron. Yeah, somebody throw out 1 electron, somebody. So all these group 1 element throw 1 electron out. So all these group 2 element throw 2 electron out. These elements sometimes throw 2 electrons, sometimes throw 1 electron, sometimes 3 electrons. It's hard to predict for this element. But this non-metal, most of these non-metal, fluorine, oxygen, this nitrogen, phosphorus, so this orange element here pick the electron. So let's write 1 here. So this is called oxidation reaction because lithium throw out the oxygen. Now I'm going to write oxygen, and oxygen is in where? Oxygen is right here in the group 6 here. And I told you oxygen picks 2 electrons in previous class, and then O becomes 2 minus. So this is called reduction. Reduction. Everybody got that? So O, this is non-metal, that orange element, right? That pick 2 electron and become O2 minus. So this is called reduction. Lithium throw out 1 electron from its outermost orbit, and it becomes Li plus. So this kind of reaction is called oxidation. Everybody got that? Throw electron, oxidation, pick electron, reduction. Yeah. Li minus, this guy. No, it throw out because it has a negative charge, and it throws that negative charge out, and it becomes plus.
Yeah, so what is the minus?
Yes, you can write the minus here.
No, like Li minus.
Oh no, so basically what I'm saying is Li was like this tongue here, and then it throws out this part, and this one just I caught that electron and throw out. Yeah, make sense? So I pick that part and throw out, right? Good, good, like that. It's easy to write this way. So you will definitely see some definition in exam. Oh, I will put, oh, what is called oxidation? So I will leave 4 statement and find the definition of oxidation or something like that. Yeah. So that's important here. So, I have some time here. So I'm going to, there are some rules to identify, to calculate the oxidation number of some element in some compound. So there are these rules. So if there is H, the oxidation number of H is +1. Always, yeah, we need to, this is always like fixed, yeah. H cannot have more than +1 oxidation state in our course here. If something is sitting alone and has not thrown out electron or has not picked out electron, just like Li, in this case we call oxidation number is 0. It's sitting there and doing nothing. It has not thrown electron out. It's not combining with other. It's just sitting alone. In that case, oxidation number is 0. So if there is a fluorine with some compound, the oxidation number is given as -1. Not alone. If fluorine is alone, so this is alone. So Li alone. So if it is alone, the oxidation number is 0. So if fluorine is sitting with something else like this, let's say Na2F. So in this case, fluorine has oxidation number -1 here. Sorry, NaF. So oxidation number has of fluorine is -1. But if fluorine is sitting alone like this, in this case, it is 0. Make sense? So somebody is sitting alone and has not done anything. In that case, oxidation of that guy is 0. So all these periodic table elements are 0 state. Now they are in 0 state. Have you got that? Like that. So alone is 0. If it is with some combined with some compound, F is counted as -1, and what else? Hydrogen is +1. Oxygen is -2. So if we have oxygen there with some compound, like let's say I have CO2. So the oxygen is here with some compound. In that case, oxygen is taken as -2, -2, and that's it. So let's look one more. And so the sum of all the oxidation number in one compound is 0. So let's say I have this Na2O. So if the oxidation state of this guy, the oxidation state of another Na, the oxidation of state of O, if I sum all the oxidation number of this compound, that should be 0, like that. Yeah. So these are the rules, and we'll follow these rules and calculate some oxidation state of some element. Yeah. So these are the rules. So the rules are in the slide number 17. Each atom in pure element, so it has not combined with anything else, sitting just alone there, right? That is 0. Yeah. And then if fluorine is there with somebody, and that fluorine has -1. If oxygen is sitting with somebody there, that is counted as -2. Chlorine, chlorine, bromine, iodine, group 7 element, -1. If there is a hydrogen sitting with somebody else, hydrogen is counted as +1. And if you count if you sum all the oxidation number of this element here, and that should be equal to 0 here. So we will use these rules and calculate the oxidation number of some elements. So I'm going to do one problem here, and I will show you what I'm talking about. A2Cr2O7. So what is the oxidation state of chromium Cr2 there? So that's the question here, right? So look here. Where is potassium? Potassium is right in the group 1 here. So group 1 element has +1 charge, right? So we need to write +1. So I'm going to write K is a +1. So +1, and I have two potassium here. So I'm going to multiply with 2, like that. And chromium, I don't know what is the oxidation state. So I just assume that is X. And I have 2 chromium here, so I'm going to multiply that with 2. So I might put like that here. And oxygen is sitting with somebody else, and you can see here oxygen is, if oxygen is sitting with somebody, that's a -2. So oxygen here is -2, and there are 7 oxygen atom here. So like that. So you see that? So now the sum of all is 0. Now I just solve for the X. So let's do that one. 2 multiplied by 1 is 2, plus 2x, and then 2 multiplied by 7 is 14. There is minus plus is -14. So you can just put in calculator, and then this is 0 here. Now 2 minus 14. So this is plus 2x. 2 minus 14 is 12. Minus 12. Just put in calculator. So this one and this one is -12 equals to 0. Now take 12 this way. So plus 2x is equals to -12, like that, and x is equals to, this 2 comes down here, -12 by, I think this is -12, this -12 comes this way, that's plus 12, so plus 12 by plus 2, right? So that is equals to 6, so plus 6. So Cr there is in +6 oxidation state. So this chromium here has +6 charge, that means. So that means that. Everybody got that? So basically, all this element of group 1 has +1. All of these elements, when in compound, group 2 elements have +2. And this aluminum most of the time is free. But these elements have different kind of sometimes 5, sometimes 6, sometimes 2. So we should be calculate the oxidation number. How many charges is there, like that way. So we will do some practice in next class, and we will finish this. You got that? So hopefully you learned something. So it's a lot, yeah? It's a lot. Thank you, everybody.